Once the gearbox is completed, we can move on to installing the clutch and primary drive. A new seal has been fitted to the inner clutch cover, which is now fitted into place. This particular oil seal is there to stop dirt, dust and chain lube from entering the clutch chamber, and it does not actually seal any lubricant, so smear its lip with grease now so it doesn't run dry in service. Insert and tighten the 3 screws that hold the cover in place. A Woodruff key is fitted onto the gearbox main shaft. A smear of grease is also applied to the seal surface of the reconditioned clutch hub, which is now fitted to the main shaft. A clutch hub holding tool is used to secure the hub while the nut is tensioned. If you don't have this tool, you could select top gear and use a piece of chain attached to the end of a steel bar to stop the shaft from turning by securing the gearbox sprocket instead. Either way, the nut is tensioned up to 60 foot-pounds. If there is one thing that stands out as being critical in a Trident engine rebuild, it's the clutch and primary drive. Get these right and the bike should be a dream to ride with a transmission that provides years of trouble-free service. Get it wrong and you'll have a bike that is much harder to ride. It will vibrate badly, and every time you open up the primary drive you will find premature wear and tear. Since the clutch is the next component to install, let's have a look at it now. It is unorthodox in that it's a dry, single plate unit sandwiched between the gearbox and the primary drive. It can work perfectly, but it must have been manufactured and set up exactly as it was designed. There are 3 main problems you can encounter with the Trident clutch. Firstly, the workshop manual states the minimum lift required to disengage the clutch is 35 thou. However, there is only about 22 thou lift available with a standard clutch lever. If the clutch is set up perfectly, it will disengage completely with 22 thou lift, but if not, it will require more, and as a result it will drag, making gear changes, neutral selection and stops in traffic very difficult. To overcome this, an inexperienced Trident owner will adjust the clutch cable so there is no free play in order to get more lift. However, that solution actually causes the second problem: premature thrust bearing wear. The bearings that were designed to carry the side thrust, generated only when the clutch lever was pulled in, end up carrying that side thrust all the time. This leads to premature wear of the thrust bearings and sometimes even causes bearing seizure, which causes the pull rod that disengages the clutch to shear off. It's then a major job to remove the clutch to fix the problem. The third problem with the Trident clutch is that it can cause considerable vibration if it's assembled and installed without selectively fitting the components. Due to manufacturing variations in the components, a Trident clutch can easily have run-out problems, and since it is a heavy clutch, a little run-out can cause a lot of vibration. Let's look at the clutch and go over what you need to do to get it right. Here's the complete clutch assembly, and here are the individual components: flywheel, pressure plate, diaphragm spring, friction plate and end cover. You'll notice that the 2 heaviest pieces have been drilled for balance purposes. I think we can assume that the supplier would have balanced each clutch as a complete assembly. So if you have reason to believe nobody has been there before you, you should mark the components before disassembly so you can at least initially rebuild it as it was originally assembled. You may then find it needs tweaking, but that will give you a starting point. If you didn't mark it prior to disassembly, you may be thinking you should have your clutch checked for balance once it's back together again, but there are more obvious things you can do to make sure you will have a smooth runner. You can have a perfectly balanced clutch that causes severe vibration if you don't take the time to make sure it's running true. Now, we mounted the T160's clutch end cover in a lathe to demonstrate what I'm talking about. Here you can see that the ring the diaphragm spring pushes against is not running true to the mounting face. You can also see that a clutch mounted to this end cover should run out badly in a lateral direction. The amount of run out here is quite alarming when you consider the weight that will be spinning it up to something like 4,000 RPM while attached to it. Before you start machining your end cover so that it has no run out though, you may be amazed to find that by selective assembly and installation of the clutch, it's quite likely you can get it running true without machining anything. I discovered this by accident. After pulling the clutch out of another of my Tridents to replace a leaking oil seal, I forgot that I had selectively fitted the clutch during the rebuild I had done years before. On reassembly, the bike vibrated badly. It had previously been really smooth. I dismantled it again, found I had ignored my previous assembly markings, reassembled it with my markings realigned, and it returned to silky smooth operation. What I'm about to demonstrate may surprise some Trident owners. You need to recreate the way the clutch will be mounted when in service. The easiest way to do this is to use your inner and outer primary covers together. You should fit the clutch in each of the 6 possible spline positions and measure and record the amount of run out in each position. My T160 clutch has 14 thou run out when fitted in the worst possible spline position. By testing the 6 possible spline positions and measuring the run out in each one, you will find the best final assembly position to give you the smoothest operation. For my T160, the best position gave only 4 thou run out, which is much more acceptable. A clutch tested from another Trident had run out that varied from 16 thou to 7 thou. Here you can see my test results for each of the 6 positions. Clearly, if you ignore this, you are just leaving it to chance regarding the level of vibration your clutch will produce. And vibration is not the only negative possible outcome. The localized loading on the clutch splines caused by the imbalance could also accelerate wear of those splines as they support the clutch while it is engaged. You should now be able to see how important it is to selectively fit your clutch to eliminate unnecessary vibration. That's problem 3 sorted out. Let's now turn our attention to problem 1, the issue of making the clutch release with as little lift as possible. Remember, if we get that right, we should have no problems with problem number 2, premature thrust bearing wear. You have just seen that the surface the outer lip of the diaphragm spring pushes against on the clutch end cover may not be concentric with its outer diameter, and therefore quite likely not concentric to the opposing ring on the pressure plate that the inner lip of the diaphragm pushes against. When the pull rod is drawn outwards to release the clutch, the pressure plate should lift away from the clutch plate evenly. For this to happen, the spring needs to be applying even pressure around the entire circumference of the clutch. If it has more pressure in one place than another, it will release unevenly, which means more lift will be required than necessary to fully release the clutch. It is easy to test if your clutch is releasing evenly. Let's assemble this one and I'll demonstrate. Place a spacer ring on a flat surface. I'm using the one from my Cush drive. Place a centering tool inside the ring and then lower the flywheel onto the ring. Note the centre punch mark made prior to disassembly. Place the clutch plate onto the centering tool with the lip facing down. And then lay 6 strips of paper onto the clutch plate using the slots in the flywheel to space them evenly around the circumference. Lower the pressure plate onto the centering tool. Now I've aligned the markings that I made previously. The diaphragm presses against the pressure plate with the inner lip against the machined ring. I use paint and texture pen to mark the previous location of the diaphragm against the end cover. Place the end cover onto the flywheel, making sure to also align the centre punch marks made previously. Insert all 12 bolts till finger tight and then tension them down against the diaphragm spring, no more than 1 turn at a time, working your way around the clutch until they are all pulled right down. Remove the centering tool. Now we can test for even lift. I'll install the pull rod, but to stop the bearing from rotating during this test, I'll insert the rod through a thick washer that is very close in dimensions to the bearing, so it will bind the inner and outer races together. The pull rod must engage with the bearing to ensure that it pulls exactly as it will in service. Run the clutch shaft nut into place. Drop a suitable spacer onto the pull rod that will allow you to then run a nut onto the threaded end of the pull rod so you can disengage the clutch. The clutch plate spline protrudes slightly beyond the flywheel, so use the ring you used earlier to support the entire clutch unit, allowing the clutch plate to be free for the purpose of this test. The pull rod's thread has a pitch of very close to 40 thou for each turn of the nut, so we can easily tell how much lift it takes to release the clutch plate. Place a ring spanner onto the nut ready for the test. I'm using a dial indicator to get a more accurate measurement, but if you don't have one you will still get very close just observing the spanner movement. So I rotate the nut just over 3/4 of a turn to give me 35 thou lift. According to the workshop manual, all 6 strips of paper should be free. Unfortunately, only 3 are free to be removed. I increase it up to 40 thou lift and check again, but still the 3 strips are held. At 45 thou lift, 1 more releases, leaving 2 to go. At 48 thou, finally the remaining 2 strips of paper are free. This clutch is going to drag badly as it requires more than twice the available lift for complete disengagement. If this was a multi-coil spring clutch such as fitted to a Trident Twin, you would simply adjust the springs to get the clutch to lift evenly and move on. But with a diaphragm spring clutch there is no such adjustment. We already saw that end covers have quality control issues. It's almost a certainty that the diaphragm was not manufactured perfectly either. So if you can match discrepancies in the end cover with discrepancies in the diaphragm by testing a number of different positions, you will identify the best position and hopefully be able to create a clutch that releases evenly. I tested a number of different positions with this clutch without achieving a satisfactory outcome though, so I decided to check the pressure plate for discrepancies. I measured the thickness between the friction surface and the ring the diaphragm presses against in a number of different locations. There was a variation of 5 thou, which is quite significant considering there is only 22 thou lift available. A form tool was used in a lathe to take a very light cut off the surface of the ring to correct this. I reassembled the clutch using the markings from my previous best test outcome as a guide and ran the test again. Here is the result. "22 thou to release all strips of paper. This will now be a great clutch. Gear changes will be smooth, stopping in traffic will be easy, and selecting neutral while stationary will be a breeze. I'll be able to set the pull rod end clearance correctly so my thrust bearings won't be under constant load during operation, and they will last much longer as well. Taking the time to get this right is paramount, and once you've found the best assembly position, make sure you mark everything in case you ever need to pull the clutch apart again. I have noticed with a number of T160s that there was damage to the seal holder on the inside of the inner chain case, consistent with the clutch end covered tab washers or bolt heads making contact with the seal holder during operation. So make sure your tab washers are tapped down snugly, and since the primary chain alignment in the next step determines where the clutch actually runs in service, make sure you keep this in mind when setting that up to avoid this from being a problem. Of course, if this was a T150, it would not be an issue because there is no gear lever crossover shaft seal holder. Once the clutch is assembled correctly and you have marked the best spline position for smooth running, it's time to fit the pull rod without the washer that was used to lock the thrust bearing in our test. We can then install the clutch onto the clutch hub. Now we're ready to fit the inner primary chain case. New needle roller bearings and new oil seals have been fitted. Sealant is applied to the new gasket around the crankshaft, oil pump cavity and breather cavity, and the cover is slid into place. Insert and tighten all bolts and screws, not forgetting that some are inside the primary case and some are outside. In my next video we check out how to install the oil pump, the primary drive, and for T160 owners, gear shift setup and a solution to the unavailable replacement primary chain.